So we had our first test was 1-1 to 1-6, and 1-1 to 1-5, and then our second test will be from 1-6 on, okay? Next Tuesday, you're going to have a quiz on 1.6, which is end behavior and what we're learning today. That's going to be on Tuesday, September 24th, and it's on, do you guys say College Board or AP Classroom? College Board? Does it? If I say either one, you guys know the difference, right? Like it's the same thing. I'm just going to put on CB, which is College Board, okay? You don't have school Monday, all right? So today we're going to do 1.7 just for one day. Tomorrow's 1.8, and then we start 1.9, 1.10, and so on. You guys don't have school Monday. Tuesday I have to have a dental procedure done, so I won't be here. It makes me so mad. It's a 5-minute procedure. 5 minutes, and they only do appointments in the morning. So I'm so frustrated. But anyway, I have to do that. So I have a sub on this day, and since it's on College Board, you need to bring your laptops on Tuesday. And since it's online, well, most of my quizzes are online. You know, we've had some in class, of course, and we still will, but a lot of them are online, and I don't always give you class time to work on it, like a day dedicated to it. You could always work on it, like when homework is done and all that stuff. But anyway, I'll give you like a week to do the quiz on your own time. And anytime the quiz is online, obviously you can use your notes and stuff because you're doing it outside of class. I obviously can't control that, so I don't even try. So anytime we have an online quiz, even if I give you in-class time, you can use your notes and work together. So I'll make sure I tell my sub that you guys can work together and have open notes for this quiz, okay? It's on College Board. It's an actual quiz. You'll find it the same way you found the assignment yesterday. It'll be right in there, okay? And it'll be open longer than just that day. It'll be open for like, I don't know, I think I have it open for a whole week or something like that. But you might as well get it done in class so you can move on. So I just want you to know it's only going to be these 2 sections, even though we'll be moving on from them. And I'll remind you about this on Friday, but maybe mental note, write it down. You need your laptop on Tuesday. I think a lot of you bring them every day anyway, so no big deal. Okay, so moving on to this new stuff, we will finish it in class. You'll have a lot of time to work and ask for help if you need it. So let me just tell you what we're tackling today. We're beginning to tackle is something called rational functions, and we work on it in like 5 sections. They're pretty deep, okay? They have so many moving parts. There's so many differences to it. Like when we learned about lines, the most like basic function, it had a slope and a y-intercept. Ooh, once in a while it would be horizontal or vertical. We learned how to graph it, but it was really it. It didn't have anything special going on, okay? Rational functions have a lot of parts. So today we learned just one little piece. Tomorrow we'll add and we'll keep adding. And a big part of rational functions is end behavior. So we'll be reviewing the end behavior of these functions, or just how to do end behavior by learning these, okay? And so let's talk about what a rational function is. It is a function, clearly, and it's a ratio of 2 polynomials. Let me write one down right here, just so you can see what one looks like. You've seen them before. They're a type of function we cover in Algebra 2. We're going to cover all the same stuff and go a little bit further. But this is a rational function. A ratio means fraction. So this is the ratio of 2 polynomials, a poly on top and a poly on the bottom. So anytime we have fractions in any kind of math problem, there's always some tricky stuff because there's certain numbers you can't have in a denominator, or one certain number, which is 0. So that's where a lot of the trickiness comes in, okay? But today we're not graphing them. We're learning about the asymptotes and the end behaviors. Actually, there's 3 types of asymptotes: horizontal, vertical, and slant. Today we're talking about horizontal and slant asymptotes, okay? All right, so let's talk about that. We decide the, let me tell you what an asymptote is. That might be important. You might remember that funny word from Algebra 2. But an asymptote is an imaginary line on your coordinate plane that your graph approaches but does not touch or cross. There's one exception to the rule that we do cross the asymptotes, but I'm just hold that nugget, put it away for now. For now, let's just say asymptotes are imaginary lines on a graph that you can't cross or touch. Why do they exist? Well, let me just try, and I'm going to scoot over to a piece of paper once in a while. You don't need to write this down. If I gave you the most basic type of function known as a line, you guys would graph it by doing a y-intercept and the slope, or using your graphing calculator or table of values, however you would graph your line, okay? But I think you guys would all agree with me that this is a picture of this. This is the function, the algebraic function. This is the picture of the algebraic function. This represents this represents that. They're the same thing, two different representations of the same thing. Well, what asymptotes are the visual representation of some rational function, and because of the trickiness of there being a fraction, there are places on the graph that on the coordinate plane that your graph can't touch for reasons we'll learn later, and those are called asymptotes, okay? So, but for now, we're not worried about the graph of it, we're just worried about actually finding it. Later, we'll put them on the graph. So we tell here we're talking about horizontal asymptotes first. Horizontal asymptotes we find by looking at the degree of the numerator and the degree of the denominator. So for example, this is a degree 1 over a degree 2. So anytime the degree of the numerator is less than the degree of the denominator, the line y equals 0 is the horizontal asymptote. All horizontal lines start with a y equals something. Okay? So if you look, 1 is the degree of my numerator, 2 is the degree of my denominator, 1 is less than 2, so my horizontal asymptote, like we just said, is y equals 0. HA, abbreviation for horizontal asymptote. Notice there's a y, so it's K, because later we'll do vertical asymptotes, and those are x's. So to help you remember, we always put y equals whatever the number is. Okay? Another type is if the degree of the numerator equals the degree of the denominator. Like an example would be right? The degree of the numerator is 2 and the degree of the denominator is 2. 2 equals 2. They're the same. Whenever that happens, we write a ratio of the leading coefficients. Guys, the word ratio is just fancy talk for a fraction, okay? Ratio means a fraction. So whenever I say, oh, okay, my numerator and denominator are the same, the degrees are the same, I then grab the numbers out in front of those. And I always simplify a fraction. That's 8 over 2, which is what? 4. So my horizontal asymptote here would be y equals 4. Okay. And lastly, if the degree of my numerator is greater than the degree of my denominator, I would have no horizontal asymptote. You won't have one. Here's an example. So my numerator's degree is 2, and my denominator's degree is 1, and 2 is greater than 1. So where if it was like fill in the blank, we would say none. Doesn't exist. There isn't one. Okay? But sometimes in this situation, when there's no horizontal asymptote, we will have something called a slant asymptote. So whenever we get an HA of none, we have to go one more step and say, okay, but does it have a slant asymptote? And just like a horizontal asymptote, a horizontal line looks like this. A slant asymptote is a regular old line that has a slope, which makes it slant. So, just a line. Y equals 2x plus 5, whatever, okay? And so the way, I said sometimes we will have a slant asymptote. The way to tell, and this is something else we have to know, if the degree of the numerator is exactly 1 more than the degree of the denominator, like the example I just gave you, 2 is exactly 1 more than 1. In other words, if you subtract the two of them, what should you always get? 1. So if the degree of my numerator is 100 and the degree of my denominator is 99, do I have a slant asymptote? Yeah, because this difference is 1, okay? If this was a 5 and this was a 1, you'd say no slant and no HA, okay? So once we decide, yes, there is a slant asymptote, we have to find it. And the way that we find it is doing something called long division. Okay? And so what we are going to do is actually divide this ratio of polynomials. There's so many different things we can say about this. This is a fraction, it's division, it's a ratio of two polynomials. But remember what I just said a second ago? It's also division. That's x squared minus 5x plus 4 divided by x minus 2. So if you had me for Algebra 2, you learned how to do this. If you had Mrs. Shackton, you learned how to do this. I don't know if Miss Baldock taught it. I'm not going to say anything about that. I just don't know. But I'm going to review it. And this is one of those skills that we use it pretty rarely, but we have to know how to use it. Okay? So to teach it to you, I'm going to remind you what you learned in 4th grade, okay? In 4th grade, and you don't have to write this, okay? In 4th grade, you learned how to do long division, and you hated it then as well. Let's make something, okay? And you haven't had to do a problem like this in like forever, because we use calculators at this stage of our math career. But for to know how to do polynomial long division, it helps to remember the steps for regular old integer division. So here we go. What we would do is say, does 8 go into 3? No. Does 8 go into 37? Yep, it does. 8 goes into 37. As close as we can get would be what? How many times? 4, right? Because 8 times 4 is 32. So notice where I put the 4. I put it over the 7. That means I'm going into 37. And then remember the next step would be 4 times 8 is 32, and you put that right here. And then what would we do? Subtract. We'd subtract first, right? Subtract, and then bring down. Is it coming back to you like a little nightmare? A little bit? And then we start over. 8 goes into 51. As close as we can get would be 6. Multiply, subtract. When there's nothing left to bring down, that would be your remainder, okay? So those same steps I'm going to do right here. Little bit different, but for the most part, the same. All right, so first thing is you want to be kind of neat. Having this in neat, nice little rows and columns is going to help you. And the way we start is with the first two terms, okay? So we have x and x squared. You have to zone out everything else. Ignore everything else in the problem. And you ask yourself, what's x squared divided by x? Just like I did, what's 37 divided by 8? An easier way to think of it, though, with letters is what times x gives me x squared. What would that be? X. Now, where I put that x matters. Just like I put the 4 over the 7 because I was going into 37, I'm going to put my x over the term that it's family with, okay? It's like term. And remember, the next step was multiply. We did 4 times 8 is 32. We're going to do the same thing, guys. We're going to do x times whatever's out here. That involves the distributive property. You can either do it in your head or write it out. In the beginning, while I'm going over this, I like to just write it for you. So I'm just going to find some space, but you don't have to. So that's x times x minus 2. And distribute. Right, I would get that. That goes right here. So I did x times x is x squared. X times negative 2 is negative 2x. And remember, the next step was to subtract. I'm going to subtract as well. But guys, with polynomial subtraction, you would think about it. You have to subtract the whole thing. And instead of like putting parentheses here and drawing all this, think of it as when I distribute a negative to both terms, it just changes both signs. Both signs have to get changed. So if it was positive, it becomes negative. If it was negative, it becomes positive. That's what happens when you multiply something by a negative, which is what we're doing here. If I did it right, those first two should always be opposites and cancel. Subtract the other two terms. Negative 5x plus 2x is negative 3x. So we're at the step right now where we were with the 5. The next step was to bring down. We have something to bring down. Plus 4. Okay, don't just bring down 4, bring down the sign in front of it. A sign in front of a number stays with that number. And we start over. So this is where a lot of students will get lost. So look, you are always doing this x, but instead of going into x squared, we already did that one. We're going into negative 3x. What times x gives me negative 3x? Negative 3. Okay, so again with the distributive property, almost done. That would give me negative 3x plus 6. Change both signs. Change, change. If I did it right, those should cancel. And 4 plus negative 6 is negative 2. So I have a remainder of negative 2. Before I write my final answer, I want you guys to notice how everything lined up, all my like terms lined up. These are my squared terms. These are my linear terms. All of them are x to the first. These are all my constants. Those are the numbers without letters. If you are doing it right, that should always happen. Your columns should line up with all like terms. If not, something went wrong in your problem. Okay, so the slant asymptote here would be just the y equals x minus 3 without the remainder. You throw the remainder away. Okay, we only keep the linear part. Don't know where they came up with that, but we just go with it. We'll practice another one in a second. We're going to practice all of this right here on this next page. Okay, so if you missed a step, you'll catch on here. Edgar, your phone. You need to put your phone up, please. Okay, so here we are going to find the HAs for these three. So you are going to start learning in your brain, horizontal asymptote means I look at the degrees. There is some memorization. We have to know that, okay? And then furthermore, which one goes with which, okay? So horizontal asymptotes, I look at my degrees. The degree of my numerator. So this one looks kind of funny. What would the degree of my numerator be? What is it? 0, not 1, okay? This would be x to the 0 power. How many x's do I have? 0 of them, okay? What? Oh, sorry, thank you. Yeah, you're going to miss some stuff. Got to be fast. Guys, I really want you to wait in the future to go during homework time. But Edgar, you missed the whole first 15 minutes of the lesson. So the degree of my numerator is 0. The degree of my denominator is 2. 0 is less than 2. So my horizontal asymptote will be what? 0. Don't write 0, write y equals 0. Yep. Memorization. When it's less than, it's y equals 0. Memorize it. And the next one, if there's no number, it's a 1, right? X to the nothing power is x to the 1 power. 1 equals 1. So in this situation, we grab the leading coefficients. 3 is my leading coefficient on top. 1 is the leading coefficient on the bottom. So my HA is y equals 3 over 1, excuse me, simplified down to 3. And this last one, numerator's degree is 2, denominator's degree is 1. 2 is greater than 1, so you would say none. Does it have an SA? Yes, because the difference between those two is 1. But we're not going to find it. We're going to go find one down here. Okay, but if it had asked for find horizontal and slant, we would have found the slant here. So this one, yes, it does, but we're not finding it. Okay? Let's do one more long division in the notes. Right here. So find the slant asymptote. So right away, let's just do B. Right away, we notice that the degree of the numerator is 1 more than the degree of the denominator. Okay? That means we do have a slant asymptote. So we're going to do our long division. Knowing how to start is important. So we ask ourselves, what times x gives me 3x squared? That would be 3x. Notice where I put it. 3x times x is 3x squared. Distribute. Okay. Don't forget to change both signs in the next step. Everyone remembers this one. And I try to use different colors so you can see that it's another step. Everyone remembers this one, but a lot of people forget to change the sign of the second one as well. So anybody that's positive becomes negative, negative becomes positive. Those two should always cancel. 5x plus negative 6x is negative 1x. Bring down, if there's anything to bring down, and there is. And we start over. Still use, this guy is always going to be used. He's used always, but now we have a new first term that we're going into. What times x gives me negative x? We already know because we're lining everything up neatly. It better be a constant, a number without a letter. So x times negative 1 will give me negative x. Yeah. What am I doing? That's not it. Negative 1 times x plus 2 is what I'm doing. Negative x minus 2. Change both signs. Change that one, change that one. These two will always cancel. There's my remainder, although I don't really care about the remainder for this problem. My slant asymptote would be y equals 3x minus 1. Okay? Last thing we have to talk about, let's take a moment and appreciate these notes. These are great, how they're printed for us, word problems and graphs and all these variables. Everything's nice, and we didn't have to hand copy anything. There's a lot of positives to these notes, but there's some negatives. And sometimes I'm not real, as you've noticed, I gripe about it quite a bit. I'm not too happy about the way she did this last example. So just so you know, I'm going to extend these notes, for example 3, into the homework to show you some other types that can happen. Okay, so what I'm getting at here, this will make more sense once we get to the homework too, is it's asking for the end behavior. So we're going to practice what we learned in 1.6, which is limit notation, saying is it up, up, down, 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 up, whatever it is. Okay, but we're going to do it with rational functions. So we should recognize these as rational functions simply because it's a fraction with a poly on top and a poly on bottom. Poly on top, poly on bottom. The first step, this is what I want you guys to do. Anytime you have to find end behavior of a rational function, find the HA first. Even though it's not asking for it. It will in the homework, okay? But I'm going to make a connection here for you. Sometimes horizontal asymptotes are called end behavior asymptotes because they are tied together. They have a relationship. And I'm going to prove it to you, like I said, in a minute. But just kind of getting you started on the idea. My numerator is 5, denominator's degree is 3. 5 is greater than 3. So what would our HA be? None. We don't have one. Anytime your HA is none, you're going to have to do this step I'm about to show you, okay? Which is really simple, but what we need to know is what is the degree and the leading coefficient, but we have 2 of them, right? So what we do is combine them. You take the numerator's leading term, which is 2x to the 5th, and your denominator's leading term. Now, leading term means the term with the biggest exponent. Sometimes it's not given to us in the right order. You have to make sure you find it. So don't always just grab whatever comes first. You'll see that in the second example. Simplify this. 2 over 1 is just 2, and then what will I do with the 5 and the 3? Subtract them. So now we just do our end behavior according to this. That's it. So just like we learned the other day, and then we practiced Friday, Monday was on the progress check yesterday, whenever we have an even number degree, that means our end behavior is going in the same direction, up, up, or down, down, right? And then the 2 makes us, since it's positive, means we're going to go up, up, right? That's my end behavior. This graph's going to look crazy, but in the middle, the ends I know are both going to go up, up. So let's practice writing our limit statements. We have a left and a right. And as I've been really trying to make sure you are clear on, is this is non-negotiable. You have to write your limits this way, your end behaviors, using all of these notations in all the same exact spots that I'm doing it. This is not one of those concepts that next year a different teacher will tell you something else, or, oh, some teachers do this. This is how they're written always. That's why I'm really hammering it into your brain. Okay, so left end behavior, right end behavior, named the function by its name, and we already said it's infinity up to the left and to the right. Okay. This one's just like that one. We have an HA of none because my numerator's degree is 4, right? It's not in order, but negative 5x to the 4th is my leading term. He got pushed to the back of the line, but he's still the first. He should be in front. And then the x. 4 is more than 1, so we would have no HA. So we had to take our leading terms and simplify. And now we can tell our end behavior just by looking at that. My degree is odd, which means my end behavior will be opposite. Whenever I have opposite end behavior, I think about a line. If I had a negative 5x to the first, that would be a line with a negative slope, right? So even though this isn't a line, my end behavior will do the same exact thing. It will start up and down, just like a negative slope of a line. Okay? Limit of g of x as x approaches negative infinity and positive infinity. Up on the left, down on the right. Okay? So that's how we do it if our HA is none. And I'll tell you, that's the last 4 problems of your homework. It's just like this. Okay? So this is numbers 13 through 16. Okay, but what happens when you have an HA? That's where I'm going to show you what to do when we get to this homework right now. I called the progress check yesterday, I called it A18 just for the grade book. So that's why this is A19. And I'm going to do 1 and 2 with you to kind of extend the notes a little bit instead of creating more problems and more notes for you. I just figured I'd do the ones in the homework. It's simple. It's really simple. Really, really, really simple. So in 1, 2, 3, and 4, what they're asking for us to do is find the end behavior and the HA. Remember what I said, anytime you have to find the end behavior of a rational function, you want to do the HA first, okay? So let's find the HA of this. Okay, horizontal asymptotes, I find them by looking at the degree of my numerator and the degree of my denominator. So this is 1 on top and 2 on the bottom. Okay. Jefferson, you good? Okay. 1 on top, 2 on the bottom. 1 is less than 2. What will my HA be? If you wrote 0, you'd get it wrong. Y equals 0. Yes, I know. I'm being a pain, but I don't want you to lose a point. Okay? That's memorization. We learned at the beginning of class. Guess what? Look, because you'll miss it if you even blink. Sometimes horizontal asymptotes are called end behavior asymptotes because they dictate what happens at our ends. And this graph is going to really help us understand it. There is a horizontal asymptote right here. Guys, look, it's right there. Remember what I told you? An asymptote is a imaginary line that your graph approaches but doesn't cross, and it doesn't touch it. It gets as close as it can to it. So let me look at it closely. As I'm going towards negative infinity, right? As my x's are going to the left, normally, if there was no asymptote, we could see it's going up. But that bounds it. There's no without bound on this. It is bound by the 0. That's as close as we're going to get. It's very hard for human brains to understand, including mine, or I'll just speak for myself, my human brain, to think that I can go to the left forever. My grandchildren, my great-grandchildren, my 12 grandchildren, whatever you want to call that, could sit there and draw this line to the left and never reach the end, forever, and ever and ever. But what we do know is that it will never get above this 0. The numbers will get teenier and teenier to the point where we can't draw it. I already can't draw much closer to the 0, and our brains can't even conceptualize how small those numbers are. but those y values just get really, really small, but never, ever touch 0 or any positive numbers. And it's the opposite here. It will never go down. So you are bound by that 0, okay? So look here. We have a degree of 2 on top, a degree of 2 on the bottom. Those equal each other. So my horizontal asymptote will be y equals, somebody, what will it be? 3, yep. 3 over 1, which is 3. 3, 3. See why is the defined best first? It's when there's none. When you say none, that's when you have to do that leading term stuff that we did right here. And you will see that in problems 13 through 16, like I said. But 3 and 4 are just like these. So go forth with joy in your heart working on these, and I will come and help you. And just know we're going to add to this each day. So if you're not here, you definitely need to be watching videos, or if you missed anything, you need to review anything, definitely want to. Garbage. Not garbage. Why do you have that question here? Yeah. If it was